Hello everyone. So in this session, I'll just go through the frequency analysis. I'll consider the basic tuning fork as an example. I'll be taking two softwares into account, one is SolidWorks simulation and the ANSYS, and accordingly we'll deal with this analysis. So I'll browse the tuning fork here. Okay. So here you can directly activate the simulation tab. If you have the license of the simulation, you can directly access that tab here. So this is how easy you can switch here. You can directly create the study. So before that, even here in the answers, you just need to use this particular model analysis to deal with this kind of frequency analysis. So engineering data, you can vary over there, you can define the materials and all. Right now I'll keep it as it is. So I'll import the material first. Geometry, sorry. So you can directly select the location where you have placed it. So once you define it, you can cross check the material database here. You can edit the material database, and here the structural steel by default it got selected. If you want to change the material database, you can able to change it, but right now here in SolidWorks you could see we have applied the chrome stainless steel into account, right? So according to that, if I cross check the material properties here, could set as an elastic modulus is 2 into 11, fine. So the Poisson's ratio should be changed, so I'll make it 0.28 for now. Okay, and the density should be approximately 7800. I'm not considering these things into account for now, to just to deal with this analysis, to deal with the frequency. This is more than enough for now. Okay, elastic modulus and the Poisson's ratio is fine. Yeah, so you can directly switch to the project here, and then so the both side material have been defined and the geometries are ready to deal with this. Now I'll utilize the definition, so I can define the model here, and even same thing here in the SolidWorks. You can directly select the frequency analysis, and it is very easy here, and it is very handy to deal with this. So already we have assigned the material, so it is automatically taken into account. So here it is the mechanical workbench, it is separately opens in ANSYS. Okay, now first thing is to deal with the mesh. So I'm gonna use the mesh setting as default mechanical one. So element order, I'll use the quadratic, and here SolidWorks by default take the tetrahedral mesh into account. So I'll use the normal mesh, no changes by default. This is fine. And here in the sizing, I'll just use the fine mesh. Element size, you can able to define it manually, but I don't want to define it here. You can use your element size. Let me see how exactly it looks like. If I generate the mesh, that's fine. So it is adaptive there. You can even choose the curvature based. Accordingly, you can generate the mesh. So if you want to again still closely validate the same, you can even define the same element size, and you can go ahead. But for now, it's approximately same. Let's deal with the definition. So analysis type, the number of frequency modes, I'll select only 5 here, and you can directly solve it for that. And here also I'll do the same. I'll simply select the properties, and I'll even select the number of frequency modes as 5, and I'll run the study. So we haven't fixed anything, just remember that they are independent to move. Okay, if I just select these things, and in the list resonant frequencies, you could see all the values are approximately 0, because it is free to move. The degrees of freedom is completely 6, so it will try to restrain all the 6 degrees of freedom here. So to get the results on the 7th mode, you're gonna get the approximate displacement, I'm gonna just select the 10 modes here, and here as you have seen, all the resonant frequencies are approximately 0, and it is same here. If you want to see, this is how you can see, approximately 0 everywhere, right? So now to encounter this one, so in the analysis I'll just increase the number of modes to 10, and I'll just resolve this model, and even in SolidWorks I'll do the same. So you can see how fast we could able to generate the results here as well as here also. So if I just deal with the results now, the resonant frequencies, you could see on exactly 7th iteration we have the 443 Hz. The normal tuning fork, it has the natural frequency of 443 Hz, 443.87. So if I just use the same here to deal with this, the results, you could see it is 443.8. So approximately same. So if you want to plot these all the steps, before that what I'll do is I'll just change the boundary condition. I'll apply the fixtures here to deal with this. So I'll apply the fixed support on this region, and even in SolidWorks also I'll do the same. So you can apply the fixtures, fixed geometry on this face. Okay, now according to this we'll see what happens, and here also I'll do the same. Okay, and once I fix this, and if I just see for the results, the list resonant frequencies, you could see at exactly fourth step only it has given fourth mode 443.8, right? So how we can just see here, and I'll just cross check here, and here also it is same 443.83, isn't it? And to just validate the same, I'll just use the first 4 modes and I'll generate the modes for these here, and you can simply solve it again. Okay, so here you could see it is the fourth mode. Okay, and here also I'll just switch to the fourth mode, and this is the fourth mode here. And if I animate these two, you could see they are approximately same. Not approximately, completely same, 443.8 Hz and 443.8 Hz. So here, so this is how you can deal with the frequency analysis in both the softwares. Both are okay, and the results you could see by using the tetrahedral meshing, you could able to generate the same results in any of the platform. So this is how we can just generate this kind of analysis in both the softwares. To conclude this, what we can say is frequency analysis is generally carried out to cross-check the resonant frequencies and the number of modes according to the practical behavior of the component. We're gonna predict the natural frequencies of the components. So that's all about this session. Thank you. Stay tuned.